Welcome to VideoAssist. This video looks at the problem of placing a satellite into orbit. How much energy does it take? It references Unit 2, Section B, Activity 3, Example number 2. Make sure you read that example before watching that video. The question is this: if you had a rocket on the Earth, how much speed does it require off the launch pad so that it can go and circle the Earth, or in orbit, at 550 kilometers above the surface of the Earth? The question then is, how much speed does it need as it comes off the launch pad? The strategy is to compare the energy here and the energy here. The two energies must be the same in a frictionless environment. All that happens is that some of the kinetic energy is converted to gravitational potential energy, and so in general. So let's come up with two expressions, one for the total energy here, one for the total energy here. Then we'll let them equal and solve for the unknown V. Let's go to the surface of the Earth at the launch pad, or actually immediately after launch. What do we have in terms of total energy? Well, the total energy after launch is going to be made up of kinetic energy plus gravitational potential energy. Now, the kinetic energy is given by 1/2 mv squared, and the gravitational potential energy is, in general, negative gm over r. Let's see what we know. Well, the mass of the satellite, we need to know that, and that was given in the problem. Mass of the satellite is 1,500 kilograms. Okay? Velocity, that's what the question is asking. We don't know that. G, this is the universal constant. The universal constant is 6.67 times 10 to the negative 11. Look it up. M, that's the mass of the Earth. That's also known, 5.98 times 10 to the 24. This is the mass of the satellite, 1,500 kilograms. R, what does it stand for? It stands for the distance from the center of the Earth. So we are at the surface, so R would have to be the radius of the Earth. So I could put a little RE here, meaning we're interested in the radius of the Earth. We actually know that, or can look that up. The radius of the Earth is 6.38 times 10 to the 6. So in this expression we know everything except for V. Now, we go to the extreme and we look at what's the situation while it's in orbit. Well, the total energy should be the same, but its kinetic energy and gravitational potential energy will be slightly different from what it was on the Earth. Well, the total energy will be made up of those two, kinetic and gravitational potential energy. Let's write expressions for both and see what we know. Hopefully we can calculate that there will be no unknowns in this part of the question, because we want to compare it with what we worked out over here, and remember, V was an unknown. Okay, let's go through and see what we got. 1/2 m is the mass of the satellite, which is 1,500 kilograms, and V, we don't know the speed of, this is the speed in orbit. We don't know that. So a little aside here, we can calculate the speed in orbit going back to the previous lesson, which said that for satellites the universal gravitational force, gmm over r squared, is equal to mv squared over r. Now that's true from the previous lesson for calculating the speed or position of a satellite. I can rewrite this way, and I'll show you why. mv squared, if I multiply both sides by r, will equal gmm over r. Now this mv squared is the same as the mv squared here. So do we know these values? G is, of course, the constant, 6.67 times 10 to the negative 11. Mass, that's the mass of the Earth. You can look that up, 5.98 times 10 to the 24. This is the mass of the satellite, which is 1,500 kilograms. And R is the new radius, the position that this satellite is, the distance from it to the center of the Earth. Well, what would that be? I'll put this as R max, or R extreme. R max would equal the radius of the Earth, that's from here to here, which is 6.38 times 10 to the 6, plus 550 kilometers. Now don't forget, we have to switch 550 kilometers to meters, and so we do know what R max is. So we know what this is, we can calculate this, which is equal to this, which allows us to put it into here. So we do know the kinetic energy of the satellite while in orbit. Now we also have to know this. We have to subtract the potential energy while in orbit. G is the constant, m is the mass of the Earth, which we know, m is the mass of the satellite, and r is this value here, r max, in this case, the radius of its orbit. So we should be able to work out a number for this value, and I'll just let it be that. To solve and finish the question, we're going to take this part over here and we're going to compare it with what we have on the right hand side. Remember, we know everything over on the left side except for V. We're going to let it equal this value here and solve for V. Now, to actually see the numbers that are substituted into the equation, go back online and look at example number 2.